All right. At this point, let's explain what these electron configurations things mean. What are we doing? Are we really seating people at a concert? How does that apply to electrons? Well, let me give you a helpful hint. I'm going to go ahead and take this out and slide this back down and show you what's happening. What I've done is I've taken all the main things that you have to know and I put them into a storyline to make your life easier. Let me see if I can explain. If I go ahead and put the other half of the nucleus on, if this is the nucleus of the atom, what you have is ring 1 of the atom that goes all the way around, ring 2 that goes all the way around, ring 3, and ring 4 that goes all the way around, and 5 and 6 and 7. You'll notice there's no gaps between ring 1 and ring 2. There's no gaps between 2 and 3, and they would go all the way around. And this is sort of the idea that the scientists understand the atom to be like, where the electrons are found. Now, it's called electron configurations because it shows where the electrons are actually seated. Just like we seated people at the concert, you are seating people, or excuse me, you're seating electrons around the atom. Let me see if I can explain a lot better. Let me say this real quick. If you understood working for me and all the rules that I gave you, up and down arrows, put one in each box, then pair them up, going in this seating chart order, then you understand everything. What I'm about to do is put it into the scientific word. So if you know the story, you got it. The other cool part is you never have to draw this again. All you need is this seating chart, and you can do everything. Let me explain. In my classes, I explain the seating chart as this. There is an order to seating. The seating is going to be S, P, D, and F, or what I jokingly call SPDF. And so it's always in that order. Now, here's all you have to do. 1S, 2S, 3S, 4S, 5S. Notice the pattern. 2P, 3P, 4P, 5P. I'm just stopping at 5 for now. 3D, 4D, 5D. 4F, 5F. Very simply, what's that number? 1, it has 1 letter. 2 has 2 letters. 3 has 3 letters. 4 has 4 letters. 5, it's S, SP, SPD, SPDF. Excuse me, I wrote that wrong. SPDF, SPDF. So it would be 6S, 6P, 6D, 6F, 7S, 7P, 7D, 7F. There's nothing after split up. SPDF, S, SP, SPD, SPDF. And all you have to do is put your diagonals in, and you've got everything that you need. Okay, so all you have to have is that seating chart. Now I'm going to make it a little smaller, and I'm going to explain to you exactly how we're going to use it. 2S, 3S, 4S, 2P, 3P, 4P, 3D, 4D. I'll go ahead and go one more. 5S, 5P, 5D, 5F. We'll stop there. It goes further than that, but that's good enough. Now, one of the rules I told you is you never, ever, ever go like this. But I'm going to do it one time so you understand some things. Back when you were in middle school, you used to draw atoms that look like this. And really, that's a wrong picture. Atoms don't look like that at all. That's how we put them on paper so that we understand it and fit it into our brain. But atoms really don't look like that. It's not a dot with a bunch of rings. What really happens is electrons go around an atom all the way around. Let me give you a better idea of what I'm talking about. It's going to do something like this. You have a nucleus and you have an electron. That electron's going to go in all directions all the way around that nucleus. All the way around. Okay? And so how do we get that on paper? Well, that wouldn't be easy to draw, so we draw it like this. Now, when you were in middle school, your teachers taught you a few things like this. The first ring of an atom only holds 2. Second ring of an atom only holds 8. Third ring holds 8. And they basically told you 2 in the first, 8 in the second, 8 in the third, 8 in every other ring after that. And that was good enough for middle school, but it's not exactly accurate. So we're going to fix that here for a second. But going on this idea, 2 in the first, 8 in the second, 8 in the third, here's what happens. If we go from left to right in the seating chart, let's go this way, not diagonals. If I went like this, so if I went across like this, that's probably the better way to draw it. And we'll never do it after this ever again. How many people could sit in that little picture from the last video in an S section? 2 people. So the whole first ring holds 2. That's the explanation of why the first ring when atom holds 2. 2 fit in the S, 6 in the P. Second ring can hold up to 8. Third ring, 2S, P holds 6. If you count back on that little picture, D would hold 10. So grand total, third ring can hold up to 18. If I counted in the fourth ring, 2 here, 6 here, 10 here. Now you have to count the lawn seating because I didn't count in the lawn seating. But if you go count in the lawn seating, it can hold up to 14 total. So if you add all that together, that's 32. And the next ring would hold 32. And the next ring would hold 32. So in an atom, the first ring can hold up to 2. Second ring can hold up to 8. We learned that in middle school. When they told us the third ring would hold up to 8, that wasn't quite accurate. But the reason is in middle school, they only dealt with the first 20 elements. We deal with all 100 of them on the chart. So we have to be accurate now. 2 in the first, 8 in the second, 18, and then it's 32, 32, 32. So the atom can hold lots and lots of electrons. Now, a little bit of a hint. Let's go back to this. 1s, 2s, 3s, 4s, 5s, 2p, 3p, 4p, 5p, 3d, 4d, 5d, 4f, 5f. That's good enough for now. We could go the 6th and 7th, but we're supposed to follow these diagonals. Now, I told you in the last video that you would never have to use that picture again, and here's why. All you need is a pointer finger and slide, and you can know what is called the electron configuration, abbreviated, of any atom. Let me explain. The electron configuration is not going to be showing where people sit at a concert. We're going to show where the electrons are located around the atom. And here's how we're going to do that. Using the periodic table, let's pick an element like element number 4, beryllium. Well, we learned in one of the other videos that beryllium is number 4. That means beryllium has 4 protons and 4 electrons. So it's neutral. What we're going to focus on are these 4 electrons. Here's how you do it. Start at the top. 1s holds how many? 2. 2s holds 2. And you're done. Because these two numbers add up to 4. Let's pick something else. Let's pick something like carbon. Carbon, element number 6. So all you do is start at the beginning. 1s holds 2. 2s holds 2. So far I'm at 4. 2p holds up to 6. But if we put a 6 there, that's 6, 7, 8, 9, 10. That's too many. So we have 2p holds 2. You showed where all the electrons are sitting. As a matter of fact, you can actually show it a little bit better by doing what's called the orbital diagram. The orbital diagram is super easy because the orbital diagram comes off of this. Here's what it looks like. It's a long box like this. 1s is one box. Remember from your picture in the last video? It holds 2 electrons. Yeah, they look like that. 2s holds 2. That's one box, and it holds 2. 2p was 3 boxes. If you're not sure what I'm talking about, look back at your picture from the last video, but it holds 3 boxes. Do you remember how do you put 2 electrons in 3 boxes? Do you put them together? No. You break them up. That shows exactly how the electrons are set up. So like I said, you don't have to draw out the whole amphitheater again, but you can do what is called the electron configuration in the orbital diagram of any element. Let's try one more real quick, then I'll let you try a few on your own. Let's take a bigger element. Let's take something like silicon, number 14. So Si is number 14. So you just start at the beginning. 1s holds 2. Slide down, 2s holds 2. After 2s is 2p, holds 6. So I have 6, 7, 8, 9, 10. I'm doing great. After 2p is 3s. 3s holds 2. And I have 2 more left. So 3p holds 2. This is called the electron configuration. 1s2, 2s2, 2p6, 3s2, 3p6. What does this do for us? Well, if I want to look, those are all the first ring. How do I know? Because it has a 1. How many are sitting in the first ring? 2. These are in the second ring. How many electrons are in the second ring? 8. How many are in the third ring right now? 4. It's simple adding. And so you can tell where all the electrons are located just by the electron configuration, except this is more accurate than doing something like this. You don't know really where they are, you've just drawn rings and put them in there. So this is a lot more accurate than the old school or old style atoms that you learned in middle school. So what happens when you take something like argon? Okay, argon is number 18. So I'm going to quickly run through this one. 1s2, 2s2, 2p6, 3s2, 3p6. Interesting thing about this, you should know from one of the other videos, argon is a noble gas. Noble gases are already full. And since they're already full, they don't need to do anything else with their electrons. What does that look like? Well, if I did the orbital diagram, 1s is 2. Now sometimes arrows are drawn like this, and sometimes they're drawn as hooks. Both ways in books, so I'll draw it with hooks to be a little faster. 2s holds 2. 2p, watch how I'm drawing this. 3 boxes. 1, 2, 3, 4, 5, 6. Then I filled it. 3s holds 2. 3p. 1, 2, 3. Now pair. 4, 5, 6. I can see it is full. So the orbital diagram comes from the electron configurations. Okay? And so you can do any element. The further up you get, the more electrons you're going to have, and the further down this diagram you're going to have to use. All right? So in the next video, I'm going to have you practice a couple on your own. Let's see how you do.